Hypothesis testing. The learning outcomes include summarize units of analysis, compare and contrast cross-sectional and longitudinal studies, build hypotheses to solve problems, classify and interpret collected data, develop guidelines for testing hypotheses, analyze and test hypotheses, and recommend how to design research studies so that they are relevant to managers or other groups. The units of analysis are what you're interested in learning about. They may be at the individual, group, or organizational level. For instance, here is a shopping cart. We want to know about the customer and what they want to buy. We also want to know information about what is in stock at the city and state and region levels so that we can restock as needed to ensure our customers get what they need. At the same time, we need to understand what our supplier has available and what we need in terms of products. The units of analysis we use here will depend on our perspective and what problem we're trying to solve. When gathering data, you may choose to do a cross-sectional or longitudinal study. A cross-sectional study is completed at one point in time, is quick and cheap, but does not capture differences over time. Longitudinal data adds more than one data collection time period to the analysis. The data collection is rich, but is expensive to gather and interpret, is time-consuming, and suffers from participant mortality. By mortality, I don't mean that participants get hit by a bus. Instead, they don't show up on one of the data collection days, or they opt out at some point, leaving you with incomplete data. Both are good and bad. You have to make the best choice for your study. Once you actually get the data, you have a lot of work to do. You have to clean it up by editing, find any mistakes that are easily correctable, and make notes so that you can report how you reconciled inconsistencies. You have to decide how to deal with responses that are missing. If a respondent answers everything except question number 8, do you include the other answers and exclude the missing response altogether, or do you exclude the entire response? If less than 10% is missing and you have a sufficiently large sample size, you're probably okay methodologically. Then you have to code your categorical data. For instance, if you ask if employees were managers or non-managers, you might code managers as 1 and non-managers as 2. You have to do this for every non-numerical value. This is a non-trivial matter. Often, you collect data to test hypotheses. A hypothesis is a prediction of what you think is true based on theoretical background. Hypotheses are not written as questions, but as statements. They are testable relationships, e.g., 2 variables are related to each other. 1 variable causes another. 3 groups differ, etc. 2 or more variables are included in a hypothesis. You should form hypotheses after you have observed, researched, and planned, but before you gather data. You don't want data to guide the hypotheses in most situations, but theory to drive the hypotheses. Hypotheses state the question and answer and why you believe it to be true. As mentioned, you should make most hypotheses in advance based on theoretical reasoning. Use an alpha level p-value of 0.05 unless instructed otherwise. Choose the appropriate statistical test to use based on the data collected and the hypotheses to be tested. And limit the number of hypotheses tested. The more hypotheses you have, the more data you will need to collect to compensate for additional data error that enters into the situation. Sorry, but we have to go back to a little bit of statistics here. Let's talk about the null and alternative hypotheses. You may see hypotheses written as if-then statements. For instance, if women have supportive mentors with an interest in technology, they will be more likely to major in IS. The null hypothesis assumes that there is no difference. That is, it doesn't matter if women have supportive mentors or not. The null could be written as having supportive mentors with an interest in technology does not increase the likelihood that women will major in IS. The alternative is written above. The alternative is what we believe to be true. The null hypothesis is considered true until something proves otherwise. The null is already accepted and can only be rejected. The burden of proof is on the alternative. The alternative is a hypothesis you believe to be true. It's the alternative to the null hypothesis. In IS research, it's not customary to present both the null and alternative hypotheses, so you should know how to interpret the findings. Hypothesis testing allows the researchers to explain relationships between variables, establish differences between groups, and helps develop a network of associations of variables for theoretical models. When using p-values to assess the significance of hypotheses, you need to understand the null and alternate hypotheses. We always assume that the null hypothesis is true. That is, we assume that there is no effect, no difference between groups, no increase in cybersecurity breaches, etc. The null hypothesis is no effect, while the alternate hypothesis is what you are really testing to be true. For instance, you might think there would be differences between undergraduate and graduate students, or there might be differences between managers and staff, or differences between baby boomers, Gen X, millennials, and Gen Z, and so forth. You start with the assumption that there is no effect or no difference, and you must reject that hypothesis to provide support for your assertion or your alternative. A small p-value, typically less than or equal to 0.05 or 5%, indicates strong evidence against the null hypothesis. So then you would reject the null hypothesis. A large p-value greater than 0.05 or 5% indicates weak evidence against the null hypothesis, so you fail to reject the null hypothesis. Always report the p-value so your readers can draw their own conclusions. Note that you don't accept your alternative hypothesis. Instead, you reject or fail to reject the null hypothesis. That's the way p-values work. P-values, in spite of what you might be tempted to say, are not the error rate. Instead, p-values are the chance that there really was no effect, but you obtained the effect due to random sample error. Assuming there actually were no differences between mentors for men and women Ukrainian IT professionals, we would expect to obtain a significant effect in less than or equal to 5% of studies. In other words, there's a 5% chance that we made a mistake by rejecting that there were no differences between mentors for men and women Ukrainian IT professionals. Assume you rejected the null hypothesis, and you should not have. That is, the relationship was not significant and you failed to reject the null hypothesis. What does that mean? Review the previous slide and think about it. Managers should always remember that no matter the p-value, there is always a chance of error, and you may need to explain statistics to people who don't understand. They need to know that it's never 100% certain, no matter what your p-value is. Here are a couple of examples. Using the information on the previous slides, answer the questions below. You should create the null and alternative hypotheses. How do you interpret the p-values? A couple of hints are given below. In summary, researchers may use different units of analysis depending on research goals, resources, and respondent accessibility. Longitudinal studies provide rich data, but cross-sectional studies may be more practical. Use the if-then framework to build hypotheses. Researchers must edit data, handle missing data, and categorize all variables. Use hypotheses to test group differences or to establish a network of associations. Hypotheses should be made a priori, usually at the 0.05 alpha level. Minimize number of hypotheses to reduce error. And communicate results in an appropriate manner depending on your audience.